Yeah, so that quiz is due today, guys, before midnight. Make sure you turn it in before midnight. Okay. Again, please don't wait till 11:58 to turn it in. If you do that, if you wait till the last minute, it's not going to be turned in properly. You're going to have most likely technical difficulties. Something goes wrong with the scanner, something goes wrong with Canvas. That always happens when people turn assignments in last minute. And that doesn't leave a good impression at all. Some people already turned it in, so good job. But yeah, make sure it's turned in. So today, and I think we are behind, we are going to begin section 11.2, which is on series. I would love to spend so much time on sequences, but I think I have exceeded the amount of time I was supposed to spend on sequences. So the epsilon definition, guys, make sure you know it. Make sure you understand it. I will not be asking you to prove a limit using epsilon definition. The definition you need to know, as I said, because it is used in proving other theorems in chapter 11. So just make sure you understand. So this is it. We'll begin series now. And you definitely need to follow, okay? You must follow. Let me send out the attendance form. A longer link today. Yes, so sections 11, 2, 3, 4, and 5 is about series. A series is an infinitely long sum. You add a bunch of terms of a sequence forever. Okay, well, sequence is infinite in size by default, and you're just adding those terms. And for example, like let's say we have the harmonic sequence added 1 plus 1/2 plus 1/3 plus 1/4 forever. The question is, does this have a value? Do we get a finite number for the sum, or is it infinite? Is it convergent or divergent? That's the question we are trying to answer. Okay, and to do that, we are going to learn about a bunch of tests that are designed to check for convergence or divergence of a series. It's a lot of fun. This topic is a lot of fun, and a lot of mathematicians throughout the history investigated different types of series, and they discovered some cool stuff. But again, a series is a sum. Oops. Let me just hold on. Let me put my book down. Okay. What was that? What was that? I don't know. Is the sum of all terms of a sequence. Yeah. So sum of infinitely many terms. Now, in the past, you might have come across different series or different sequences. For instance, someone mentioned the arithmetic sequence. An arithmetic sequence is a sequence whose term increased by a constant value. For example, we have the sequence of even numbers 2, 4, 6, 8. And if you add that, for sure, we for sure are going to get infinity. Okay, so this is not an interesting problem. If you have an arithmetic sequence, for instance, where the terms are increasing, for sure the sum is infinite. This is pretty obvious. We are not going to be focusing on those types of series, but series whose terms go down, like 1 plus 1/2 plus 1/3. The terms here get smaller and smaller. They get closer to 0. Again, the question is, does it converge or diverge? All right, so let's make sure you guys are good with the notation. We have a sequence, let me use colors here, A1, and let me use the green for plus second term of a sequence A2 plus A3 plus ... means this goes forever. There is no stopping point. You're not doing a finite sum. We can represent this series infinitely long sum using the summation notation. The summation notation is the sigma notation. Sigma here, that's why I use green. That means we are adding the terms of A sub n. Okay, n is again the index where n begins with 1 and goes to infinity. All right. That is the summation notation. I'm hoping you guys know the summation notation. Super important. And here n is called the variable of the sum. And 1, 2, 3. N is changing from 1 to infinity. It's the variable of the sum, and what letter you assign to that variable is irrelevant, meaning that I can also represent the sum using summation of k going from 1 to infinity of a sub k. Okay, name of the index is irrelevant because it doesn't matter which one of these you expand. If I expand this one, I begin k at 1. So you do k equal to 1, and then you do plus, put k equal to 2. You get exactly the same thing. This is called a dummy index. Dummy index. It's irrelevant. Changing the name of the index doesn't change anything. But here n or k, sometimes people use I or J or M, is the index of the sum. Okay, now by default, sometimes we write down the summation notation so often that we don't even bother with writing k from 1 to infinity. Okay, so a series can be written as just the sum of a sub k or a sub n. All right, we don't put, if you don't see n equal to 1 to infinity, if you don't see that, it by default means that. Okay, so this is the super lazy way of writing a series. All right, so example. So for now, for the name of the index, I'm gonna use the letter K and then later I will call it n. But example of a sum would be the harmonic sum, which is the sum k going from 1 to infinity of 1 over k. Or again, you could say n from 1 to infinity of 1 over n. And I usually do write my k or n from 1 to infinity. At some point, I might not. So again, if I were to expand this, I begin k with 1. So I get 1 over 1. That would be 1 plus, then plug 2 for k, 1/2, then 3 for k. And this goes forever. Okay, and again, the goal here is to determine if the series, if a series, not the series, converges. So the converges means that it has a finite value. Or diverges, meaning that there is no value. There might be no value, or it could be infinity. Okay, I'll give you guys a couple of interesting examples. Okay, so here we're going to learn that the harmonic sum, 1 over k, again, k goes from 1 to infinity, diverges. Okay, you get infinity. If you were to add 1, 1/2, 1/3, 1/4 forever, you get infinity. And we're going to learn later that the sum 1 over k squared. So this one, if I expand this, plugging 1 for k, you get 1, plus you get 1 over 2 squared. Well, 1 over 2 squared is 4. Plus 1 over 3 squared, that would be 9, plus 1 over 4 squared, 16, plus so on. This sum we'll learn is going to converge. And if you're taking more advanced math, which would be Fourier series, if you take a Fourier series class or Fourier analysis class, you will learn that this sum is actually pi square over 6. And this is a special sum. These are special sums. They're called, they're from the Riemann's zeta function. And it has to do something with the Riemann hypothesis that no one can prove. And there is like $1 million prize that would be given if someone. But yeah, we can actually, I know a way to prove that this is equal pi square over 6 without taking it, without knowing any advanced math. If we have time, which we're never gonna have time, I would prove it for you. But we're just gonna show that the sum diverges or converges. If the sum converges, we might be able to find out what it converges to, or we might not be able to. We need more advanced math, but mainly we just want to know if a series diverges or converges. If it converges, we most likely won't know what it converges to. We just want to know if it converges or not. We don't care about what the actual value is. Okay, so that's the intention. Does it diverge or does it converge? That's it. Okay, so let's see how this is done. How do we determine if a series converges or diverges? And guys, I need you guys to listen. Okay, for the next, whatever you do, just stop, okay, and listen. Because this part of the lesson is so vital in understanding what comes next in chapter 11, 11.3, 11.4, 11.5. So you really, really need to listen and pay attention, okay? So here's what we are going to do. We have already studied section 11.1, which is on sequences, right? We determine if a sequence is convergent or divergent. We know how to work with sequences. Let me just write that down. How to determine the convergence or divergence of a sequence in 11.1. And all we did was just take a limit. If the limit exists, then the sequence is convergent, but we know how to work with the sequence. Okay, so what we are going to do is we are going to take our series, whatever series we have, and make a sequence out of it. A series is a sum, is an infinitely long sum. We are going to make a sequence out of that. That sounds crazy, but we can do that. So here we get, we will construct a sequence out of a series. Okay, this sequence has a name. It's called the sequence of partial sum. All right, and this is how it's done. Let's say we have a series. Consider the series k going from 1 to infinity of a sub k, which again in expanded form would be a1 plus a2 plus a3 and so on. Let's say we have a series, like the harmonic series. All right, and let me just write a4 here as well, and then plus dot dot dot. Now define a new sequence, not a series, a sequence. Okay, and I'm not gonna call the sequence a sub k because a sub k is already used right here. I will call the sequence because the sequence is called the sequence of partial sums. We call the sequence S sub n. S again stands for sums, and this is how we define that sequence. We just say the first term of the sequence S is the same as A1. It's same as the first term of our series, okay? S2 now, we'll define that to be the sum of the first two terms of our series, A1 plus A2. All right. And again, if you want, you can write this in summation notation. I could write that as k going from 1 to 2 of a sub k. And so on. S3 will define that to be the sum of the first three terms of the series, a1 plus a2 plus A3. Okay, so guys, do not confuse S with A. The A sub K are the terms of the sum that you're adding forever. And these S's are again, these are partial sums. You are adding up to a certain number. Okay, so that again in summation notation would be K from 1, 2, 3 of A sub K. Okay, and the nth term, so the nth term of S, we'll call that S sub n. And let me write that n in blue, is the sum of the first n terms of our series. A1 plus A2 plus A3 plus dot, 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 up to A sub n. Okay, so you're adding, again, the first n terms of this series. So that would be the sum K starting from 1, stopping at n of A sub K. Okay, so guys, look at that and make sure you understand what we have here. Here we have a sequence. Okay, first term, second term, third term, and this is generally the nth term. You have a bunch of things that are in a certain order. You have these things that form a sequence themselves. Okay, I hope that makes sense. Yeah, and again, this is what we call the sequence of partial sums. Partial sums of the series A sub K. All right. So again, we want to know if our series, which are these terms added forever, converge or not. Now we have a sequence right here. So notice that we have a sequence, and this S sub n is the nth term of the sequence. This is what we can do. This is really cool, guys, if you're paying attention. We can take our series where K begins from 1, going to infinity. Let me put infinity in red. Okay, of A sub K. You can think of this as a limit, as the limit of the sequence of partial sums where K goes from 1 to, let me actually write that infinity in blue. Yeah, K goes from 1 to n of A sub K, where n goes to what? Guys.
Infinity?
Yes, n goes to infinity. I'll just rewrite that in red. Yeah, where n goes to infinity. Okay, so we can think of our series, think of this infinite series as the limit of the sequence of the partial sums. Okay, so you're really finding the limit as n goes to infinity of S sub n. Okay, just S sub n, sequence of partial sums. The limit of that is the same as the value of the infinite series. Okay, so if this thing converges, If this converges, then our sum is going to converge. And if you find the value of the limit, then you know what the series converges to. All right, so let's do an example. Again, I need you all to pay attention. This is a really, really cool example. When I learned about this example, my mind was blown. I still think it is really cool, this example. The sum k goes from 1, of course, to infinity of 1 over k. This example is, by the way, this example is in every book. It's in your book also, but I'm gonna still do it. All right. Let me see. Let me make sure I am paying attention to the chat box here. All right. So let's write out a few terms of this sum, just so you know what it looks like. Beginning k at 1, we get 1 over 1 times 1 plus 1, 2, plus k equal to 2, we get 1 over 2 times 2 plus 1, 3, plus 1 over 3 times 4, and so on. Of course, I can't write down every term because this is an infinite sum. And again, notice that the terms of this series get smaller and smaller. Okay, they do. So the series might converge. These terms, again, the idea is this: if the terms get small fast enough, if they diminish to 0 fast enough, then when you add them, you might end up with a finite value. Okay, that's the reasoning. If the terms don't get small fast enough, then the sum may diverge, just like an improper integral. This is actually, guys, this is exactly like an improper, what you did for an improper integral. Remember, just look at that, guys. Look at that. Remember improper integrals? Let's say we have the integral from 1 to infinity of f of x dx. That improper integral. We wrote that. Let me write that over here. From 1 to infinity of f of x dx. This resembles this series right here. What did we do to that integral? We redefined that integral using a limit. We said this is the same as the limit of the integral from 1 to call it n instead of t. How's that? You could call this, we call this t, you can call it n of f of x dx, and we took t to infinity. That limit resembles exactly what we have over here. Okay, so we are doing the discrete version of an improper integral. Okay, discrete version. Discrete is when you go with n equal to 1, 2, 3. But that's exactly what we are doing. Okay, and again, same ideas apply here. We're gonna have the P series theorem later on. Okay, but these terms might get small fast enough for the series to converge. Okay, some people say, oh, well, you're adding positive terms forever, so of course this will be infinity. No, that's not true. That's not always true. Same goes for improper integrals. Okay, so again, imagine you really have 1 to infinity of 1 over x times x plus 1. If you add that integral. By the way, the value of the integral and the series are not the same. You can't find that series by doing an integration, because integrals and sums don't do the same thing. Okay, but if I had this integral, I would do a partial fraction. It's easier to break this product into a sum, turn it into a sum. We'll do a partial fraction. It's easier. Okay, so we have 1 over, and we're going to use the shortcut, the cover method, 1 over k plus 1. This has a decomposition of a fraction with denominator k, and another with denominator k plus 1. Okay, let's do the cover method. So I want to know what goes on the numerator. I ask myself what makes this 0. K equal to 0 makes that 0. So I go to the left and I cover that same factor and I plug 0 for k. I get 1 over 0 plus 1. That is 1. And 1 is what goes on the numerator of k. Okay, if you're not comfortable with this method, you just use your method. To see what goes up here, you look at the 0 of this denominator, which is -1. So you go to the left, you cover that same factor, and you plug -1 for the remaining factor. We end up with 1 over -1, and that gives us -1, which is this coefficient. Now we have the partial fraction decomposition. So now I can rewrite the series in a much better format as the series of 1 over k minus 1 over k plus 1. Okay, same series, but written in a much nicer way. Now let's find the sequence of partial sums. I don't have to do S1, S2, S3 in S until I get to Sn. I can just go ahead and write down what S sub n is, but I will write the terms for you anyway, so you could see what's going on here. S1 is the first term of the sum, okay? And that is when you plug 1 for k. Guys, pay attention, please. So we get 1 over 1 is 1, minus 1 over 1 plus 1, that would be 1/2. That's the first term of the first term of the partial sum. And don't simplify that, okay? You don't need to simplify. Again, this is just A1. S sub 2 is the sum of the first 2 terms of the series. And that is obtained by plugging k equal to 1 and k equal to 2 and adding up. Let me write that summation notation in green. So plug k equal to 1, we get 1 minus 1 over 2. Okay, this is A sub 1, guys. That's A sub 1. Plus, plug in k equal to 2. Plug k equal to 2 here, you get 1 over 2 minus 1 over 2 plus 1. That would be 1/2 minus 1/3. Okay, so that is A sub 2. Something really interesting happens in this sum. These numbers cancel out. The -1/2 cancels out. and you end up with 1 minus 1/3. We can simplify this sum a little bit, and that's what we are doing. Let me just do one more. S sub 3 is the sum of the first 3 terms of our series. Okay, so plug k equal to 1, 2, 3, find a1, a2, a3, and add them up. I already have a1 plus I already did a2. Okay, plus plug 3 for k. Here you get 1/3 minus 1/3 plus 1. That's 1/3 minus 1/4. Let's see if things cancel out. Yes, they do. Here, -1/2 go away. We have -1/3 canceling out. So what we end up with is the very first term of the first bracket and the very last term of the last bracket. Okay, I want you to see the pattern. First term of the first bracket and last term of the last bracket survive every time. Okay, so let's just, again, this is a1 plus a2 plus a3 partial sum. This is the third partial sum. Before we had the second partial sum. Let's just write S sub n out. Okay, so S sub n, I'm just going to write out a few terms. 1 minus 1/2 plus 1/2 minus 1/3. That would be the second term. So that's a1, a2 plus 1/3 minus 1/4. So that's a sub 3 plus, again, dot, dot, dot. All right. The last bracket is when k is n. Okay. You're plugging n into your sequence function. That's what the nth term of this partial sum is. Okay, so we get 1/n minus 1/n, k becomes n, 1/n plus 1. Okay, so yeah, that is a sub n. This is the nth partial sum that we just wrote. Okay, let's simplify S sub n. Things drastically cancel out. This sum is called a telescoping sum, telescoping series, because of the cancellation. So again, remember what happened with the previous partial sums. The terms that survive, first term of the first bracket and the last term of the last bracket. Same thing happens here. This 1 and this -1/n plus 1 are going to survive. Everything else will cancel out. This -1/2, this half, this -1/3, 1/3. Okay. So look at the cancellation, guys. Look at the pattern in cancellation. For every, and guys, listen, because the same thing, the same idea is going to be applied to more complicated telescoping series. So make sure you understand what is canceling out. Given any two consecutive brackets, okay, the second term of the first bracket cancels the first term of the second bracket. Let's see that for the next two brackets. For these two brackets, the second term of the first bracket cancels the first term of the next bracket. Okay, so second cancels first. for each two brackets. For the last two brackets, but I haven't written down the previous bracket, but for this bracket, the second term of the previous bracket, which we haven't written, would cancel the first term of this bracket. That would cancel out. Okay, so for each bracket, the first term is always canceled out, and we end up with, again, 1 minus 1 over m plus 1. 1 over, yes, m plus 1. We just got ourselves a formula for the nth partial sum. I hope you understand how cool this thing is. I really hope so. So again, let me make sure you understand what this result means. This means that if I were, guys, listen, if I were to add the first n terms of the sum, I would get this. So understanding the result. Let's make sure you understand it. If I were to take k from 1 to n of this series, 1 over k times k plus 1, excuse me, I would get 1 minus 1 over n plus 1. That's what this means. So for example, yeah, question?
Do we always assume that it's going from 1?
Yes, we do. Yes, series
Okay.
by default begin at 1. Yeah.
Okay,
for sure.
thank you.
Yeah. So for example, guys, imagine someone asks you to, hey, calculate the summation k going from 1 to 10 of 1 over k times k plus 1. Someone asks you, hey, dude, you have no life. If you have no life, add 10 terms of the series. Okay, take a calculator, or not a calculator, but just sit down and add 10 terms of the series. Okay, if you're clever enough, and if you have a way to derive the partial sum, then you don't have to sit down and really add 10 terms. All you have to do is plug 10 for n. Okay, so I can either do it directly like a crazy man, one over that would be 10 times 11. Okay, I could do all of that, which would be insane. Or I can just say the value is 1 minus 1 over 10 plus 1. Okay, much easier to do, isn't it? Yeah. I remember giving a intermediate algebra exam years ago, and there was a series question where the student had to use a series formula to get the value. There are these like sum formulas. If you remember from Math 7, there are those sum formulas that give you the sum of n squared, the sum of n cubed. There was one of those questions on that exam, and students were allowed to use a calculator for certain problems. I saw this girl repeatedly punching a button on the calculator. She was pressing a button, that same button for probably 20 minutes. I am not joking, 20 minutes. And that's because there was a question asking the students to do a sum from 1 to 1005. Okay. So instead of using a formula, she actually punched it in into the calculator, 20 minutes. Yeah. And she was laughing. So I go up to her and like, what are you doing? She's just laughing. She's like, I know, I'm being stupid, crazy. And the problem worth only like 5 points for a 150-point exam. 5 points. But God has created these shortcuts, partial sums, that you can use. Okay, but let's get back to it. So this is the partial sum. Okay, now I want to know what happens to the original series. Okay, so let's take our series, which was k from 1 to infinity of 1 over k, k plus 1. Guys, this is the same thing as the limit of the sum where k goes from 1 to n. Instead, we take n to infinity. You have an improper integral, just like that. Write that improper integral using a limit, and then you integrate, plug in t, and then we take t to infinity. We are doing exactly that. Okay, so imagine this is the value of that definite integrals. 1 minus 1 over n plus 1. We just found that. Okay, right there. Our partial, and it's the nth partial sum. And now let n go to infinity. When n goes to infinity, this thing goes to 0, and you end up with 1. So we have ourselves a convergent series. Yeah, the value of this series is just 1. You are adding terms forever, and you just end up with 1. Okay, so again, if you were immortal and could live forever, so again, that would be 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot, 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 forever, dot, okay? That is just 1. Weird. Against intuition, that would say, hey, you're adding things forever and you should get infinite in the end. That is not happening. The sum doesn't go beyond 1. Okay, so we say series converges. And we know what it converges to. It converges to 1. This is an example of a telescoping series. Telescoping series is a series whose terms cancel out upon expansion. Okay? So here we can cancel out almost all terms of the series and end up with, well, so when I say almost, you end up with 1 or 2 terms in the end, at least 2 terms in the end. Okay? Yeah, there will be a bunch of telescoping series questions in the book. You're not gonna miss them. You're not gonna miss them. They're really cool. But of course, not all series are telescoping. We have the good old geometric series. I think that, again, the most important series that is out there, it is Use especially in the math of finance, probability. It has a lot of applications in probability where you're doing let's say you're doing a stochastic process, okay, like tossing coins a bunch of times, or you are rolling dice a bunch of times. But a lot of applications in finances, as I said before, annuities, savings account, reverse annuities, sinking funds. Okay, but the geometric series is basically this. It's A plus AR plus AR squared plus AR cubed, and it goes forever. So terms of this series again are, as you see, each term is R times the previous term. R is the common ratio, and we can write this in summation notation as, again, we'll go with K equal to 1, from K equal to 1 to infinity of A times R to the power of K minus 1. K here begins with 1. And you can check and see why this is the formula. If you plug 1 for K, you end up with A times R to the 0. R to the 0 is just 1, and that gives you A, would be the first term. If K is equal to 2, you get A times R to the power of 1, AR, that would be the second term. Okay? We want to do exactly the same thing with a geometric series, and I think I have enough time to do that today. We want to come up with the sequence of partial sum. So what would happen? What would we get if we add the first n terms of the series? Not all of them, but n of them. That's what we want. We want the nth partial sum. Because if I can find a formula for it, then I'll be able to take n to infinity and see what I get for our geometric series. Okay? Yeah, that would be S sub n we are looking for, guys. The sum of the first n terms, that would be A plus A times R plus A times R squared. Plus A times R cubed, plus A times R to the n minus 1. You're stopping at n at the nth term. Okay, that would be the nth term. Okay, so this is what we want. And again, we don't want to use a calculator. Someone says, yo, add the first 100 terms. We don't want to use a calculator. We want a formula for it. Okay, typically in algebra, if there is a pattern in the sum, and we do have a pattern, we can typically come up with a short formula, with just a couple of terms in it that will give us this whole thing. Okay, so again, someone asks you add the first 100 terms. We don't want to do that by hand. Okay, so this is our S sub n. This is what we are trying to find. I'm trying to find S sub n. There's a trick we are going to use, okay, to find S sub n. You have this equation. Okay, I want something like the telescoping series to happen. I want cancellation. When we subtract, I want to cancel things out. So we are gonna form a second expression like this one, a second equation, so that it has AR squared, AR cubed, and so that we want to subtract. We want to subtract and get a lot of the terms to cancel out. What we do is we form a second equation by multiplying this equation by r. Okay, so multiply this times it by r. If I do that, I'll get on the left r times s sub n. On the right, multiply this by r, you get ar. Plus multiply this by r, you get ar squared. Multiply that by r, you get ar cubed. Okay, multiply this by r, you get ar to the power of 4. I'm not gonna write that, but let's just do dot, dot, dot. Okay, multiply this by r. That times r, the power of r goes up by 1, so we get ar to the power of n. Guys, make sure you understand what we are doing. I am forming a second equation by multiplying everything in this equation by r. All right. Let me. I'll indicate that right here so you know it. Multiply every term by r to form a second equation, because we can add or subtract two equations. If you have two equations, it says you have a system of equations, basically. The rules say that you could add or subtract those equations. And guess what? We are going to subtract these two equations, because when you do, a lot of the terms will cancel out. AR is going to cancel, AR squares are going to cancel. So subtract. We'll do this equation minus this equation. Or you could do this equation minus this equation. Who cares? You subtract them, you'll get cancellation. All right, so here, we'll just do minus. Okay, you subtract the left-hand side, you have to subtract the right-hand side. Okay, we'll take away the whole thing. All right, so on the left, we get s sub n minus, we get s sub n minus, there's that minus, r times s sub n. If you have two equations, you're doing operation on the two equations, you have to do the same thing on the left-hand sides and the right-hand sides. So we are subtracting these two. We subtract these two. ARs again cancel. AR squares cancel. AR cubes cancel. All right. And if you guys pay enough attention, the term before a times r to the n is going to be AR n minus 1. The powers are going up by 1. So again, the term before that is AR to the n minus 1. And that AR n minus 1 gets killed by this AR n minus 1. Okay, so that gets canceled by the term previous to AR n. And what survives? The surviving terms are A and AR to the power of n on the right-hand side. So A minus A times R to the n. I can highlight those for you. That survives and this survived. Okay. So you get this really nice equation here. And remember the goal. The goal is to find S sub n. I want S sub n, my nth partial sum. So you're gonna solve for S sub n. Because after all, S sub n is the sum of the first n terms. That's our partial sum. So factor S sub n from the left hand. You get 1 minus r equal to, on the right, you can factor the a if you want. It's just nicer that way. Okay, and since I'm solving for S sub n, I have to divide by 1 minus r. So S sub n is a, 1 minus r to the n, divided by 1 minus r. Now you can probably see why r can't be 1. We talked about that. If you have a geometric series, r cannot be 1, because if r is 1, you don't have a geometric series anymore. It makes the fraction undefined. So again, what is the meaning of this formula? It's really cool. If someone asks you, hey, add the series where k begins with 1 and ends at n of a times r to the power of k minus 1. So again, this is a plus ar squared plus all the way to ar to the power of n minus 1. This is just a times 1 minus r to the power of n divided by 1 minus r. So if someone gives you a geometric series and says, add the first 1,000 terms, you're not going to take a calculator and spend days to add 1,000 terms. Instead, you put 1,000 for your n. And that gives you just a 2-second calculation that can substitute a 3-day calculation, you know? Yeah. Now, we have the partial sum. We have the nth partial sum. This is our S sub n. So I can take its limit to see if it converges or when it converges. Sum k goes from 1 to infinity of ar to the k minus 1. This is the limit as n goes to infinity of the partial sum. And we just found a formula for that. Let me see, where do I put that? I will put that right here. That's the limit as n goes to, I just need a minute to finish this thing. Yeah, we just found a formula. The formula is a 1 minus r to the n over 1 minus r. Okay, and the convergence of this thing depends on what r is, guys. It depends on r. If you go back to the section for sequences yesterday, I just need 30 more seconds. Remember what we said about a geometric sequence. Okay, if you have a geometric sequence, its convergence depends on the ratio. If the ratio is a number between -1 and 1, then r to the n or r to the n minus 1 goes to 0. Otherwise, it's not gonna have a limit. Okay, so there are two scenarios to this. If absolute value of r is less than 1, if r is between -1 and 1, then what happens is that as n gets big, r to the n goes to 0. Imagine you have 1/2. Imagine r is 1/2. You have 1/2 to the n. this would go to 0 when n goes to infinity. The fraction gets smaller and smaller. Okay. So again, if you have a ratio between -1 and 1, this thing goes to 0, and you end up with a over 1 minus r. Yeah, r to the n would go to 0 for that value. For r between -1 and 1. Otherwise, nothing. Otherwise, this doesn't have a limit. Okay, if r is anything else, the limit does not exist. We're not going to get an answer. So this is a DNE for absolute value of r greater or equal than 1, including 1. Okay. All right, so we'll continue on Monday, but a geometric series is convergent if the common ratio is between -1 and 1, is what this is telling us. If the common ratio of it, and that makes sense. It just makes sense. Imagine you have a geometric series that goes like 1 plus 2 plus 2 squared plus 2 cubed plus 2 to the 4th. Of course, this thing is going to diverge. It's getting bigger and bigger because the common ratio is more than 1. The terms don't get small. We want the terms to get small geometrically fast. And that will happen if the ratio is between -1 and 1. You get that as the sum of the geometric series. Guys, go over the book, please. Section 11 to read that section during the weekend. Read the notes. Try to do as many homework problems as you can for this section. And I will see you on Monday.
I have a question.
Yeah.
I saw this thing where it was the summation of all positive real numbers, 1 plus 2 plus 3, all the way to real numbers.
Yeah.
-112.
It's 1/12, something like that.
Yeah, -1/12. How is that possible?
You don't ask me, man. Those are, I did not take attendance, Alex. I didn't. That thing is so it goes something like 1 plus 2 plus 3 plus this goes forever. And
Yeah,
it was -1/12.
Yeah.
You know what? I haven't yeah, I saw it. Wait, that's again, that has to do with one of those cool things that some assumes makes an assumption somewhere. I haven't looked at the proof, to be honest with you. I haven't looked at it. Like
Right.
I heard people say that before, like this -1/12, and of course it's not believable. But there is a proof that you get -1/12, but that proof probably makes a certain assumption that you need to kind of pay attention to. If you make a certain assumption in that sum, you are going to end up with -1/12.
Right.
It's like the sum. Let me actually hold the recording here.